Okay, let's get going. Sequence and series, day 2. Day 1 sequences were all arithmetic. They were very similar to linear functions, and we had a good time with those. These sequences, if you looked at these sequences and said, this is my first term, this is my second, third, fourth, fifth, and you put it in table form, right? Second term is 6, third term is 12. You would see that we would be looking at a table that represents an exponential function. And so we're very familiar with exponential functions. They have a multiplier. Sometimes that multiplier is greater than 1. Sometimes it's less than 1. And so sometimes it's between 1 and 0 and 1, so it's fractional. And so we're used to working with exponential functions, just like we were used to working with linear functions. But in sequence land, this is not called an exponential function. It's called a geometric sequence. And so it's the same idea, though. There's a multiplier, and I think if you look at this, we can all see that the multiplier is 2. Every term is being multiplied by the term before it, n times 2. So 3 times 2 is 6, 6 times 2 is 12, etc., etc. So instead of a common difference, we have a common ratio. Why would they call a multiplier a common ratio? It's because if you take any term and divide it, so if we take 12 and we divide it by the term before it, we get a ratio, right? And that ratio is common no matter what term you pick. If you take any term, divide it by the term before it, we're going to get the same ratio, which is not 1/2, which is 2. So that's why 2 would be called our common ratio. So we indicate our common ratio by an R. So R is 2. And so just like the arithmetic sequence, the geometric sequence comes with its own formula to define it. And so its nth term formula, why don't you go ahead and write this above our title, Sequence and Series Day 2. Our nth term formula is a sub n equals a sub 1 times r to the n minus 1. You will have your formula sheet for your test, but by the time you're done with doing all of your work today, you'll have this one memorized anyways because you'll use it so often. So here we go. To find the nth term definition that describes this geometric sequence, we're going to put our first term, which is 3, and we're going to plug in our common ratio, and we see r, and that's it. So let's say we wanted to know our fourth term. Well, we already know it's 24, but if we plugged a 4 in for n, we'd get 2 to the third power, which is 8. 8 times 3 is 24. Woo woo. This formula works. And so let's have fun. These next few are just very straightforward like this. We do have a multiplier. You can see every term is being multiplied by the term before it times 3. And so our multiplier is 3. Another way to think about it is our common ratio. 9 divided by 3 is 3. So our common ratio, which we write as r, is 3. Our first term is given to us, right, which is 1. It's nice because with arithmetic, we had to use our table, or we did use our table to find our 0th term. And in this formula, we don't need the 0th term. So it's a little quicker, and we just go ahead and plug that in. Our first term is 1. Our multiplier, or our common ratio, is 3. And minus 1, let's clean that up and write it like this. And this formula will give us any term we want for this very specific geometric sequence. So the same thing for number 3. This time our multiplier, or our common difference, is going to be fractional, right? Some of you can see right away, oh, we're just multiplying each term by 1/2 to get the term, the following term. And another way to do it, once again, common ratio, take your 50, divide it by the term before it, and that gives me my r is 1/2. Obviously, my first term is given to me, and I'm going to put these together into my nth term definition, which says do your first term, your multiplier raised to the n minus 1, and this will give us any term we want in the sequence. Pretty straightforward here on this second day. All right, here we see an interesting sequence where the terms are oscillating back and forth between positive term, negative term, positive term, negative term. That tells us that we have an r that is negative. We don't even have to think about it. Some of you, once again, are looking at this and you can tell what your R is right away. Good for you. For the rest of us, we're going to go ahead and take that negative 1/4, divide it by 1/2. Either use your calculator or the knowledge that, right, that 4 goes down here, that 2 goes up here. That's negative 2/4, which is negative 1/2. So that is our R. Our a sub 1 was given to us. That's 1/2. Put it all together, and we get that our formula is 1/2. Negative 1/2 raised to the n minus 1. Feel free to slow this down, hit pause. I actually just finished doing this same tutorial, and it took me 20 minutes, and I found out that it did not record the sound. Apparently one of my little, what are those things called on the side of your computer, is not working. So I'm going to try to do this as quickly as I can because I have to move on to other things. So pause me, slow me down, do what you have to do. I'm flying through this. All right, number 5, find the fourth term of a geometric sequence that has the following. So what am I going to do here? I'm going to go ahead and just define this particular geometric sequence. I'm going to say, well, they gave me my first term, they gave me my R, and now they want me to find the fourth term. Okay, I'm going to go ahead and find the fourth term. So another way to write the fourth term is a sub 4. So I'm going to go ahead and put in 4 when I see the n. So let's see, I could either put this straight into my calculator, or I could say 4 minus 1 is 3. 1/2 times 1/2 times 1/2 is 1/8. 1/8 times, I'm sorry, 1/2 times 1/2 times 1/2. 2 times 2 is 4. 4 times 2 is 8. That's true. 1/8 times 1/2 is 1/16. And there we are. I'm trying to catch up with myself. Okay. So does that look good? Oh, I'm sorry. This is why it's not turning out right. I'm going way too fast, right? My first term is not 1/2. My first term is 1/3. You're probably going, Miss Overby, slow down. All right. So 1/2 to the third power is 1/8, but 1/8 times 1/3 is 1/24. I knew that didn't sound right since I already just did this whole lesson just a minute ago. All right, the fourth term of a geometric sequence is 125, and the 10th term is 125 over 64. We can tell right away that our R is fractional, and that this is a decreasing sequence. And so what we're going to do is we're going to turn to our table to get a visual of how to set up this equation. I'm going to go ahead and go through. I don't know the first 3 terms, but I know the fourth term is 125. And then my next term that I know is that 10th term. The 10th term is 125 over 64. And so to set up the equation I'm going to work with, I'm going to use a common sense equation that says, hey, I know what my fourth term is. I know I do something to that fourth term to end up at the 10th term. So when we were looking at this type of problem with arithmetic sequence, I would say, oh, I've got 1, 2, 3, 4, 5, 6 jumps to get from my fourth term to my 10th term. And each jump is worth a D. So I would say a sub 4 plus D plus D plus D plus D. Eventually would say a sub 4 plus 6D equals a sub 10. But this isn't linear. This is not arithmetic. It's geometric. So let's think about what each jump actually means in this case. It means with my first jump, I would take 125 and I would multiply it by my common ratio. The second jump, I'd multiply that again by my common ratio. So all these jumps, each jump I would be multiplying by R. So if I wanted to write it out the long way, I'd say, well, to get from a sub 4, the fourth term, to the 10th term, I have to multiply the fourth term times R times R times R times R times R, 1, 2, 3, 4, 5, times R. And of course, a much more efficient way to write it would be R to the 6 equals a sub 10. So that's where we get our formula from, looking at the table. And so we do know these things. We know a sub 4 is 125. We don't know R. That's why we're setting up this equation. A sub 10 is 125 over 64. We want to isolate 125 by dividing both sides. We can think of this side as multiplying by the reciprocal. So we isolate R to the 6th, We cancel that out. And here we have a choice. We can go ahead and take the natural log of both sides or log of both sides, bring that 6 down. You can do it that way if you want. Or you can just kind of use logic and say, okay, what fraction raised to the 6th power is going to give me 1 over 64? And yep, you got it. It's going to be 1/2. It usually will be something that's pretty obvious. You can use natural logs or logs if you want to, but that's not going to be necessary for this section. So 1/2 times 1/2 times 1/2 times 1/2 times 1/2 times 1/2 is indeed 1 over 64. So there we have it. We use the same idea of this, the table and the jumping and questioning what each jump means to set up our formula. Then we plugged in what we knew and solved for what we didn't know, which was the common ratio. So very similar strategy to what we used on the first day. All right, now we're going to go ahead and move on to taking the sum. And to take the sum for a geometric series, it's going to look different than taking the sum of an arithmetic series. It's going to be a different formula. Once again, you'll get this on the test, so don't freak out. And really, the formula is pretty straightforward. If we want to take the sum of the first 8 terms, that's what the S sub 8 means. It means that my n is 8, right? A sub 1 is obviously given to us, so we have a 9. R is given to us, so we're going to just plug and chug, right? N, once again, for this problem, it's going to be 8. And then we have over 1 minus 0.4. We're going to put that into our calculators. Let me flip it over so I don't have to put it into my calculator, and we'll get a decimal that goes on and on and on, and we'll write it as 14.99. Now, the second part says, now write the problem using summation notation. So summation notation means that we're going to use a new symbol called sigma. It is a Greek letter. It's a capital sigma, and it's indicating that we're going to take a sum. All mathematicians know when they see a sigma, oh, this indicates we're taking a sum. In this particular type of sum problem, we're going to tell the reader who's looking at this summation notation where to start. And we're going to say, start with the first term. So n equals 1 means we're starting with a sub 1. And then where are we stopping the sum? Well, in this case, we're stopping at 8. So this tells the reader, the sigma says we're taking a sum. The n equals 1 part says where we're starting. We're starting at a sub 1. And where we're stopping, a sub 8. And then we go ahead, after the sigma, we tell the reader what sequence we're dealing with. And we don't give this information that we're given up here, we give it in formula form. So we're going to say our formula is, just wrote a negative. So our formula is a sub 1 is 9, and r is 0.4 to the n minus 1. So the cool thing is when somebody sees this, it's exactly saying the same thing as all of this. So pretty cool. And next class, we're going to go ahead and do something cool with this with our inspires, and we'll wait till next class. All right, so 8, it's also a sum formula, but instead of like 7 was a partial sum, right? With 7, we were just taking the sum of the first 8 terms, yet a sequence goes on and on forever, right? So number 8, we're looking at a sequence that goes on and on forever, and we're being asked to take the sum of that sequence as it's going on and on forever, which is kind of crazy. It's asking us to take a sum of something that still isn't done yet. It's mind-blowing. So we've got a formula that we're going to use, and this indicates that we're taking the sum of an infinite amount. We're taking the sum of the full series, even though it goes on and on forever. All right, I'll stop obsessing about the craziness of what we're doing. A sub 1 in our formula, that's the first term, which is -6. What's our common ratio? The easiest way to find it is to do 5 divided by -6. So our common ratio, so we're going to 1 minus our common ratio of 5/6. We're going to put that into the calculator, and we're going to get that our infinite sum is -36 over 11. Crazy. Even though this series is continuing to progress on and on and on as I speak, we already know what the sum of this infinite series is. Crazy. All right, let's write it in summation notation form. So when you see this, this means that we're going to use the sigma, the Greek letter, and we're going to indicate where we're starting. We're starting with n is equal to 1, so we're starting with the first term. And where are we ending? We're really never ending. we're going to there's not really an infinite term. We're just going on to infinity. And once again, we're going to state what our definition of this geometric sequence is. And we're going to put our first term and our r, and we're going to raise it to n minus 1. And once again, even our calculators are going to help us to find an infinite sum. Okay, I'll check on the time here. All right, your parents decide to pay you an allowance. Finally, there's only one catch. They pay you 1 cent the first day, 2 cents the second day, 4 cents the third day, and so on. If your daily allowance keeps on doubling, because that's what it's doing, right? 1 penny, 2 pennies, 4 pennies, what will your monthly take be for a 31-day month? So some of you, this isn't going to be surprising, and others of you, once again, can I use the word mind-blowing again? It's going to be crazy. All right, so here we go. We're taking a sum. So, because they asked what will your monthly take be, so another way of saying sum. And so we're going to do a partial sum, right? We're adding up the first 31 days, and then we're going to go ahead and use that sum formula, which says a sub 1, so my first day is 0.01, 1 cent, and then I'm going to multiply that by 1 minus my r, since I'm doubling, right? If I wanted to do it the old-fashioned way, divide the second term by the first, I would still get 2. So we're doubling my r, my common ratio is 2, and we're going to raise it to my n, which is 31, and we're going to divide it by 1 minus the common ratio. Well, if I put this into my calculator and hit enter, it's crazy. You know what your allowance is going to be for that month, for that 31-day month? Let's see, $21,474,836.47. I think you should try to convince your parents to go this route for your daily allowance. That would be kind of fun. All right, homework is from the book. Please take the time to do your practice, because practice is the only way that our brains can cement the learning that just took place now. Without practice, in 24 hours, your brain will remember maybe 10-20% of this. So practice is essential to learning. So practice and check your answers, and I will see you in class. Thanks for joining me.